independent versus dependent events, and the multiplication rule. If two events are independent, it means that one event does not affect the probability of the other event happening. Two events which would be considered independent would be rolling a die and flipping a coin. Whether or not the die lands with the 3 showing has nothing to do with the coin getting a heads showing. One event does not affect the other. An example of two events that are considered to be not independent, otherwise known as dependent, are being under the age of 16 and being a high school graduate. Graduating typically means that you're over 16, probably 17 or 18. So if you happen to be under the age of 16, chances are you are also not a high school graduate. So those two events would be considered to be dependent on one another, so we can say they are not independent. Here is our example of our two independent events. We have event number 1 with one favorable outcome, that is, getting a 3. One favorable outcome. Event number 2 is a coin. How many outcomes are on a coin? Yes, 2, a heads and a tails. So event number 2 also has one favorable outcome, and that favorable outcome is the heads itself. The dice could have a possible 6 different numbers turn up, and the coins could have a possible 2 different numbers turn up. So, how do we work out the probability? We're going to use the multiplication rule. The multiplication rule simply says if two events are independent, we can take the probability of each event on its own and simply multiply them together. Since probability equals the number of favorable outcomes over the number of equally likely outcomes, we can easily set each problem up to be multiplied together. 1 out of 6. There is one favorable outcome of 3 out of 6 possible rolls. And we're going to multiply that by the probability that the coin comes up as heads, 1 out of 2. Multiply them together. In fractions, multiply across the top and multiply across the bottom. So the probability you arrive at is 1 over 12. And that, as a decimal, is approximately 0.0833, where you take the calculator and do 1 divided by 12, and 0.0833, moving the decimal 2 places to the right, makes it into a percent at about 8.33%. You can also use an area model to represent probability. Let's say you are given the following numbers: 2, 3, 4, 5, 6, and 7. This is a total of 6 possible outcomes. All of them are equally likely. You can figure out some probabilities by using an area model. So first we would place it in a grid. It can be a square or rectangular grid depending on what you're working with. Here are our numbers, 2 through 7. We have some even numbers and some odd numbers. Let's evaluate the following probabilities. The probability of an even number showing up. Well, how many even numbers do we have? We have a 2, a 4, and a 6. There are 3 favorable outcomes out of 6 equally likely outcomes. 3 out of 6 is equal to 1/2, which is equal to 0.5. And turning it into a percent, move the decimal 2 places to the right and filling in with a 0, that is equal to 50%. Our next example, we are trying to find the probability of a number that is divisible by 3. So looking at our possible combinations, we have 6 numbers in our pool. However, only 2 of them are divisible by 3, the 3 and the 6. So we have a 2 out of 6 probability, which is reduced to 1/3, which is equivalent to 0.3333, which turns into 33.33%. And the last one we have to do here is the probability of the number being both even and divisible by 3. Well, our even numbers are 2, 4, and 6. And divisible by 3 means one of these numbers that we circled hopefully is also divisible by 3. And when we look at it, we see that 6 is the number which is our favorable outcome out of the entire equally likely outcome set, which is 6 numbers. So the probability that a number is both even and divisible by 3 is 1 out of 6, which is equivalent to 0.1667, convert to a decimal, 16.67%. And moving on to the final example, let's say we live in a place where it rains 30% of the time. Construct an area model to estimate the probability that it rains 2 days in a row. 30% of the time is important. 2 days in a row means it has to land on that 30% twice. We're going to use an area model in order to recreate our situation. So I'm going to use a square and say that this side is day 1 and this side is day 2. If you section off the units, and we're going by percents, this is 100%, the middle being 50, and this is the end. And on the other side, you have a 50 and you have 100. You can mark off units of 10. So that each tick mark is worth 10%. If it's taking you longer to do this, you may pause the video here and catch up. Okay, now to use our information. we have day 1. Day 1, 30% of the time it rains. So on day 1, on the horizontal axis, you want to go over to the 30, so 10, 20, 30's right here, and you kind of want to draw a line up because this is going to be your 30% zone. So 30% we're going to shade of the box, kind of pretending almost the vertical axis doesn't exist. And you've got this percentage, which is 30% of that portion, since we shaded 10, 20, 30%. On day 2, so day 2, we also have 30%. Day 2's shading happens to be up the left side at the 30%, go across, and shade. So we have one of the boxes that looks like a horizontal, and we have one of them that looks like a vertical. I'm going to color this one pink over here so that day 1 kind of matches what's in the image. And you happen to see an overlap. So your overlap happens to be the zone that is favorable to both. So the question is, what's the probability that it's going to be raining 2 days in a row if it only rains 30% of the time? You're going to want to look for the overlap. So what is the area of our overlap? So for area, you use literally an area model. What is our favorable zone? The green zone has dimensions, how many tick marks, because we're all tick marks across the top and bottom, the sides, everything is tick marks. We've got a zone that looks like this. This is going to be our favorable zone. How many square units is that? Well, you've got a 3 by 3. So 3 by 3 is equal to 9. What is our total possible working space? Well, it happens to be the entire zone of 100% in both directions. How many tick marks is that? Well, it's a big square of a 10 by 10. So a 10 by 10 happens to be 100. So what is the probability, again, that it will rain 2 days in a row? 9 out of 100, which is equal to 0.09, which is then equal to 9%. Part B, what is the probability that it rains exactly one of the 2 days? Well, we can already use our model. So if it rains one of the 2 days, that means we have yes rain and a no rain. So if it rains on day 1, we could use the same vertical space to look at it. But if it doesn't rain on day 2, instead of using the 3 for the yes, we would use the 7 for the no. So the color I'm shading yellow right now is the yes rain day 1, no rain day 2 zone. So that zone happens to be 3 units by 7 units, which is 21 out of 100, which is 0.21, which is 21%. Conditional probability using a table. All of your information should always come from the table whenever you're given one. So let's see what everything is. We have rows, which are male, female, and total, and columns, which are 9th, 10th, 11th, 12th, and the total column. These are students in a high school and how many students are in each grade and their respective genders. The totals will tell you the total per grade and the total per gender, and then the total in the survey is always going to be whatever is in the bottom right corner. This is the overall amount. Okay, so let's begin. Let's find the probability that a randomly selected student is both male and in 11th grade. So essentially we're looking for a male 11th grader. So on the male line, we've got 9th graders, 10th graders, 11th and 12th. We are interested in the males that are 11th graders. So along the male line, you want to stop and see which number fits. So we have the probability that somebody is male and in 11th grade So the probability that a person is male and in the 11th grade takes the number of known males and 11th graders that we have, the favorable outcomes, and you place that over the overall, which is 2416. Taking a calculator to it to do 290 divided by 2416, you arrive at 0.12 approximately, which is about 12%. And problem number 2, you have a given that situation. So this is different. So given that means you already know something. So it's not like you're picking out of the entire overall student body. You know that the person is definitely an 11th grader. So your 2416 just got reduced by a lot. So we have, given that, the student is an 11th grader, we know that they are in an overall 11th grade pool. Well, how many people are in 11th grade? So 11th grade total is underneath the 11 in the chart. So how many people are 11th graders? 570. So we now know that our overall for this group is a selected bunch of kids, the 11th graders. So 570 is going to be my denominator. And then we want to know the probability that the student is actually male out of the 570. So out of the 570, it looks like probability that somebody is male, this vertical line means given that, the person is also an 11th grader. So given that we have an 11th grader definitely. I know my student pool is less than 2416, 70. And then the males that are 11th graders is going to be my numerator. So 290 goes up here. So the probability that a person is male, given that we know that the person we are selecting is in 11th grade, is 290 out of 570, which is approximately 0.5088, which is approximately 50.88%. And let's use the chart to see if we can get the other ones. At the bottom, here are some more conditional probability questions using the information in the table. So let's go ahead and erase some of the writing in the table so we can see what we're doing. So the probability that a person is in the 12th grade, given that they are a female, well, given that they're a female means I already know that they are in the female row over here. So the female row is 1,215. How many out of those 1,215 females are 12th graders? Well, we're looking for a number that's in the female row and also that is in the 12th grade column. So 12th graders in that column, let's try this again. 12th graders in that column are 275. So your fraction is 275 out of 1215, and that is approximately 0.2263, which is also 22.63%. And the last problem, what is the probability that a person is female given that they are in 10th grade? How many 10th graders are in this survey altogether? That's right, 617. And out of the 617, how many are female? So out of that 10th grade column, how many happen to be female? 305, right up here. So I'm going to put 305 in my numerator, take a calculator and divide it, and I get 0.4943, which is approximately 49.43%. Now you know a little bit more about conditional probability, independent events, and dependent events. And you can even use area models and tables. Thanks for listening and watching my video.